going to discuss about the techniques which are used in medical imaging. So first technique is the sound waves, right? Sound waves are used in imaging or diagnosis or in treatment. Then we have the electromagnetic devices like electromagnetic waves of low frequency, high frequency, radio waves. They are used. The third technique that is used in medical imaging, that is your nuclear radiations. So all these are used in different ways. Here the radio waves and nuclear radiations, they are blend together in one of the technique, which is called your uh, nuclear plus magnetic technique. So I will name them all one by one. Some of them are included in our syllabus, we have to discuss them. Some of them are just for your information. That is why I was asking how many of future doctors are sitting in my class, so that I can manage them with I can sync them with these technologies. So beta, all those techniques which are sound based, they are divided into three categories. One is the ultrasound, the second one is echo, third one is Doppler. So these three techniques are used to figure out the problems by using the sound waves. Okay, how many of you are aware of these names? Ultrasound, echo, and Doppler, they are very common diagnostic techniques actually in the daily life. So most of the people are aware of these all. So there are some more which are electromagnetic radiation techniques. Electromagnetic is a complete band, yani electromagnetic waves. I'm talking about electromagnetic waves. In electromagnetic waves, this there is a complete spectrum. Out of that, gamma radiations are used sometimes, x-rays are used sometimes, CT scan is used, CAT scan or PET scan. They are basically somehow different techniques. So here I have used two of them to tell you about. Then we have the magnetic and electromagnetic techniques, right? Those techniques in which magnetism and electromagnetism is involved, they are MRI, or we usually call it NMRI, nuclear magnetic resonance imaging, right? And in the above one, when I say CT scan, I mean that it is basically a sort of technique in which we use the tomographic scanning technique, right? So right, that after that, the nuclear magnetic the nuclear radiations technique. In nuclear radiations, we have one technique or one phenomena by which we perform the imaging, that is your PET scan. And PET scan is very uncommon, it is not that much common. It is called positron emission tomographic scan. Okay, positron emission tomographic scan. Usually it costs almost this. These are old notes, 1 or 2 years back, so maybe that was a rate at that time, so it would be more expensive in PKR. So PET scan is not frequently advised by the doctors, but it is a technique. Okay, so what type of questions are asked to you? Now this is the second stage of my ultrasound topic. Sorry, my medical physics topic. Before that, I told you about that what is being asked to you. What should you know about the medical physics in your daily life? The second way is what should you know in your exam. So in your exam, first of all, I would like to explain NMR or MRI is excluded. It is not included in your syllabus anymore. Before that it was, but now it is not. Now there are some question patterns from all the topics. There is very important question which is asked to you, and that is very very frequent question. working principle of all these six techniques. You must remember this. That's the largest or the highest score question in your A levels, which is asked. It is from medical physics, 6 marks. Even when MRI was in the syllabus, it was 8 marks, even, right? So in P4, it is the highest weightage question, medical physics, working principle, especially. Then some calculation based on the formulation, especially in the ultrasound. You must know about that all. So here I have just skimmed all of the topic: ultrasound, X-ray, CT scan, and PET scan. That is included in your syllabus, and you will be doing all of the working principles and calculations from these all. So here, first of all, we will be talking about ultrasound. Actually, in the sequence of the topic, ultrasound is here. It is first. Otherwise, because we have just fresh gone through the quantum, so I must start X-rays. But hopefully, it would be you people will be able to manage this all. I mean, in one or two, after 1 or 2 layers, inshallah, I will be talking about quantum. Sorry, I will be talking about X-rays. So hope that meanwhile you people will not forget about the instructions what I have delivered to you during quantum physics. Okay. Now, ultrasound is basically, yani when we divide the sound into classes or into divisions, beta, the sound between 20 hertz to 20,000 hertz, it is the audible frequency range. Those all with the frequency higher than 20,000, it is called your ultrasound. And all that whose frequency is lower than 20,000 hertz, that is called your infrasound. So we have all these sound ranges in our previous syllabus. Infrasound, ultrasound, audible sound, all is sound, right? So ultrasound will behave like a sound, but it is more powerful, have high intensity, and it has more penetration power because its frequency is very high, so it can penetrate through soft tissues even. Okay. So because that is longitudinal wave, as it is the sound family, so that travels in the form of compressions and rarefactions, right? The ultrasound travels in the form of compressions and rarefactions. So here, the speed of the ultrasound, as the speed of the sound, it increases with increase in the density of the material. As you know, all the longitudinal waves, their density increases. Their density increases when you sorry, their speed increases when you mm, uh, move them, or when you switch the sound or longitudinal wave from air to liquid, and from liquid to solids. Okay. So solids means uh, these materials in which we are going to perform ultrasound. So first of all, this, because I was talking about the speed, so I must tell you what is acoustic impedance. There are some techniques which are some technical points which are discussed in every topic, although they are linked with each other, but they are somehow different. For example, the acoustic impedance. Acoustic impedance, it seems to be a word. Acoustic mean it is linked with sound. Impedance mean the tendency or the opposition to the flow of flow, right? So that acoustic impedance is represented by Z, and Z is kg, sorry, its unit is kg m minus 1 s minus 2, because uh, that is density into speed. So density into speed, so I will extract its unit, don't worry. So here it is the product of density of the medium. It is asked to you state what is acoustic impedance. So beta, you have to remember these words or these lines what I'm going to tell you. It is the product of density of the medium and speed of the ultrasound in that medium. Or you can say it is the product of density of medium and the speed of ultrasound in that medium. But don't write it is the product of density and speed. Never, never ever. Okay, density of medium and speed of ultrasound in that medium. This is important, right? So formula is Z is equals to rho times V, and rho is the density of that medium, and V or C is basically the speed of sound in that medium. So that is why its unit can be written as kg m minus 3. This is the unit of density, and ms minus 1 is the unit of speed. So by simplifying, you get this kg m minus 2 s minus 1. So till this point, is there any confusion? Is it all clear? Okay. Now here I have enlisted few of the mediums with some of the acoustic impedance values. Here we go. If I tell you the in the first column mediums are there, and in the second column their acoustic impedances are there. Air has an acoustic impedance about 4.2 into 10 is power 2, yani 400 almost. Okay, kg meter square per second square per second. In water means gel, most of the time when we apply the ultrasound is not applied uh, through air or through any other thing on the skin. It is applied through a water gel. So that water gel is basically liquid water, but its acoustic impedance is 1.5 into 10 is about 6. Then there are soft tissues like muscles, the fat, skin. Their acoustic impedance is 1.6 exponent 6. And what about the muscles? The muscles have the acoustic impedance of 1.7 exponent 6 meters kg meter square s minus 2. And the highest acoustic impedance is the acoustic impedance of bones. So if I say that by these numbers, what do you perceive? Is acoustic impedance the only speed or the opposition to the flow? It is actually the product of both, in fact, because as I told you, that when the sound enters from air to liquid, its speed increases as well as the density of the medium increases. And when the density increased, that is why the speed increased. That is why this is the product of both of these two. Okay, so remember this concept. Now the very important topic, very important topic, the role of acoustic impedance in the ultrasound imaging. But acoustic impedance is one of the top most factor by which we define that whether the ultrasound imaging will be good, below the below average, or it would be of the average quality. So Z is determined, that is basically that determines the amount of transmitted ultrasound and reflected ultrasound in the medium. Yani this is basically, I would simply say that Z is what? Z is the ratio of transmitted intensity I transmitted to the I reflected to the I transmitted, or you can say I reflected to the I incident, right? So when we talk about this factor, I will, yes, I have a lot of calculations on this one, but in fact we will talk about intensity of the ultrasound. First of all, as the ultrasound is a wave, so believe this thing, that the waves have the intensity as energy passing through a unit area per unit time. Yani it is power transmitted by a wave per unit area, or per unit area placed perpendicular to that. So if I say that the after that I have a conclusion, but please focus on this calculation. This is very important calculation. In this calculation, what did I do? Here I naught is the incident intensity of the incident wave. That intensity is yani that wave is incident normal to this boundary of the soft tissues. This is air, and its intensity is I naught. So beta, remember this thing because that is a wave. So partially it would be transmitted into, and partially it will be reflected back. So if I want to now that IT is basically the intensity of transmitted wave, and IR is the intensity of the reflected wave or reflected ultrasound. After that, when some of the ultrasound has been entered here, that ultrasound will move on and it will reach to the next surface or interface or next boundary. Here that ultrasound yani which has been reaching here, that is transmitted and partially reflected depending upon the nature of that interface. Now, what I have stated here, depending upon the nature of this interface, I can figure out how much will be sent, how much will be received, how much will be transmitted. So if I say that the Z of the air, what is Z in the air? Z of the air is 4.02 into 10 to the power 2, and Z of the soft tissues is 1.6 exponent 6. Yes, I have stated these values. So if I write a logical equation, that equation is very logical, that out of total intensity, some of the intensity is transmitted whereas the remaining has been reflected. So I think this is not a wrong equation. But if I want to make a ratio of this all, so I will say I naught divided by I naught, I naught divided by I naught, I naught yani IT divided by I naught, IR divided by I naught. So that is what I have. I made it here, and then I made it here. So I naught and I naught will be gone, and what are you left over, or what are you left with? You are left with uh, I naught divided by I naught is gone, so you are left with 1, and here this IR will be divided by I naught separately, and IT will be divided by I naught separately. So beta, the ratio of IR to the I naught is your alpha, and ratio of IT to the I naught is your beta. These two are very very important points to remember. The alpha is actually the coefficient of reflection for any boundary. Coefficient of reflection, yani alpha is coefficient of reflection. Why? Because alpha is equals to the intensity reflected divided by intensity incident, the intensity of the incident wave. So that means that alpha will define how much is reflected, how much is incident, yani the percentage of, if I multiply that by 100, I can simply say that the percentage of reflected sound or reflected intensity is basically determined by your alpha. So is this very clear to everyone? Is it clear to all of you or not? Is there any confusion? Yes. Any confusion? Okay. Now, the alpha uh, for two different mediums is calculated here. Alpha has two equations, by the way. Oh my god, I have written this is the most important for calculations. Yani this from this point, the intensity point till this point. This is the most important thing. So I have given you that alpha is equals to z1 minus z2. You have to memorize this. There is no derivation of this equation, so please memorize this equation. Even I would request you that if you just memorize it, just like your Doppler effect, it would be given to you as well on page number 2. So alpha is z1 minus z2 whole square divided by z1 plus z2 whole square. So this is a sort of important thing, the difference of z's divided by sum of z. Difference divided by sum. Never write sum divided by difference. Right? Difference divided by z. Difference divided by sum. So difference of z divided by sum of z's whole square. This is yani देखो alpha was what, it divided by I naught. Okay, sorry, I sorry, my bad. IR divided by I naught. What was that? It was IR divided by I naught. Yani whatever the sound has been reflected back, or whatever the ultrasound has been reflected back, the ratio of reflected intensity, that was alpha. If you remember, that was alpha. Now let's have a discussion here. If you see, when the ultrasound is incident from air to the soft tissues, for to the skin, it is air, it is skin. The z for air is 4.02 into 10 to the power 2. That will also be given to you in the data. It is your z of medium 1. And what about the z of medium 2? It is 1.6 into 10 to the power 6. It's actually the coefficient of reflection, z acoustic impedance of the second medium. Okay, got it? Now plug in the values in this equation, z1 minus z2 divided by z1 plus z2, and find that number. You will be astonished that 0.999 means 99% value of the ultrasound will reflect back from the boundary. It would not be, yani it would that ultrasound will not enter in the body. Even when this ultrasound will not enter in the body, can you see that this entire ultrasound will be wasted? Yani if I say that, suppose, oh my god, just a second, suppose this is the 20 milliwatt per square meter ultrasound is being incident here. Let's say this is I naught, and very small amount will be sent into remaining all yani 19.9 into 10 raised power, sorry, 19.9 milliwatt per square meter will be sent back. So only 19.9 milliwatt, so only 0.1 milliwatt is entering in the body. And inside it has to travel a lot. For example, this is skin. So inside the skin there is a fat boundary, then there are muscles. Through that it would reach to the kidney. Let's say I'm going to have a kidney ultrasound, then it has to be attenuated a lot, then it would reach. So the problem is, if there is a huge way to go, or there is a long way to go for ultrasound inside the body, then we have to minimize the reflection and we have to maximize the transmission. Are you getting my point? Is this clear to everyone? What is my objective then? I would like to enhance alpha to 1. Enhancing alpha to 1 means there will be almost, sorry, I will reduce this alpha to almost 0. To almost 0 means z1 and z2 have greater difference, so that the ratio of reflection would be greater. Remember this thing. This question is important question, so that is I have just staring it, that why we have yani why the reflection will be more, because reflection is more because there is a difference in the z's. When there is a difference in the z, then reflection will be more. There are some remedies. Application of the gel, but when you apply the gel, it reduces the reflection. This is again a question in the past paper. Why do we apply the gel before doing ultrasound? So it reduces the reflection of the ultrasound at a significant level. Here is that significant level. For example, if I'm going to apply the gel, this is the layer of the gel, and after applying the gel, the doctor is applying the ultrasound machine. The gel has the coefficient acoustic impedance 1.5 into 10 raised power 6, whereas the skin has the acoustic impedance 1.6 into 10 raised power 6. So now I want to find out the alpha for both of them. So beta alpha is almost 1.0 into 10 raised power minus 3. 1.0 into 10 raised power minus 3 yani 0.1% of the ultrasound has been reflected back. 1 0.1%, not 1% even. 0.1%. So most of the ultrasound has been entered in the body. So this is what I required, that most of the ultrasound should enter in the body and very less should be reflected back. So that is why I have mentioned my point here, that if I want to incident more of the, I mean if I want to transmit more of the ultrasound, only 0.1 have been reflected, 99.9% has been entered in the body. This is why, because if the difference between Z1 and Z2 is very small, then reflection is less and transmission is more. So did you notice this point? Is it clear to everyone now? Now here I have given you an example. 40 milliwatt with the gel through skin, you can calculate how much has been reflected and how much has been transmitted. So IT divided by IR naught was your requirement, but you have figured out that IR divided by I naught, I can find IR divided by I naught with the help of Z's. So alpha is IR divided by I naught. So what will be the beta? Beta mean which has been transmitted out, IT divided by I naught. So beta, that will be 100% minus alpha. Yani out of 40 milliwatt, whatever has been reflected back, the remaining will be transmitted. So are you getting my point? So this is how we have this concept of ultrasound. Now I will talk about some coefficients, and almost this topic would be done, inshallah. Here, yes, the class time is up, but if you people don't have any class ahead, so please stay tuned with me, because I want to finish that out, ultrasound. So beta, in ultrasound, as I told you, that attenuation is there. One of the topic is one of the factors is attenuation. So when we have attenuation mean there is a decrease in intensity, power, or the energy of the incident wave. That is your attenuation. So why attenuation takes place? There are some factors which affects the attenuation: nature of the material, nature of the medium, coefficient of absorption, coefficient of attenuation, yani these are basically the coefficient, and thickness of the medium. The nature of the medium is defined by coefficient of attenuation, but thickness of the medium is one of the factor which tells us that whether the attenuation is increased, decreased, whatever. The attenuation is an exponential decay. What is attenuation? You have to remember that it is an exponential decay. How? Let's say I have drawn three lines. First of all, I would like to tell you that attenuation is calculated in this way. I is the incident, the intensity which has been transmitted through. It is I naught e power minus mu naught x. But this mu naught x means that if I have the same material, if I have the same thickness of different materials, one material has absorption coefficient mu1, other has mu2, other has mu3. So that one which has least attenuation, yani whose coefficient of attenuation is minimum, it would have minimum attenuation, like your skin. Then muscles have more attenuation coefficient, so their attenuation is medium. Check this one out. Intensity has been reduced to this level. And bones have the highest coefficient of attenuation, so the intensity has been reduced to this level. So that is why it is a decay. It is a exponential decay. One more thing which I want to make you clear, but attenuation is only applied when you see this type of diagram. When the X-ray ultrasound, it is said that they entered in the body or the sample and they travel through the thickness. They travel through whenever it is said that they travel through, it means there will be an attenuation. But whenever it is said that it has been incident on the interface or on the boundary, it means there is no game of trans attenuation. Here is the reflection or transmission. But when it entered in the material, then it would reflect back. Sorry, when it will be attenuated. So here we go. For example, here I have written that I is equals to I naught e power minus 28 minus mu times x. Beta, this 28 is basically mu for bones or something, some material, which is 28 per centimeter. Its unit is same, 28 per centimeter. And let's say this is a past paper question, I believe so, because I have taken the values from a past paper question. The x is 3.5 centimeter. If both are in centimeter, no need of conversion. Remember, this is another trick. If both are in the centimeter, no need of conversion. Now apply this here. I is equal to I naught e power minus 28 times 3.5. So just shift this I over here, I naught. So actually this shows that your I divided by I naught is 10 power minus 5. Almost nothing has been attenuated, you know. It means this is sorry, this is not bone. It means it is very very smooth material through which no attenuation or almost zero attenuation is taking place. So it means if I naught is transmitted from here or entering from here, then almost maybe sorry, I have used incorrect statement. I divided by I naught equals to 0.005% means the sound, the ultrasound has been attenuated significantly. Only 0.055% has been reached here. Rest all has been attenuated by this 3.5 centimeter. So for example, if we have a concept of, yeah, this is very important slide. This is a lump of skin. Some ultrasound has been incident over here. From the skin and the gel boundary, there would be some of the ultrasound reflected, some is in transmitted. So when you are going to apply the coefficient of reflection concept, it will be IR divided by I naught equals to Z1 of this material minus Z2 of this material divided by Z1 plus Z2 whole square. But when you say that some of the ultrasound has been passed through the thickness of this material, here inside the boundary or inside the sample, you will use the attenuation formula. And this is a sample. Let's say I have named it kidney. So whatever will reach to the kidney, it has undergone the process of reflection and transmission here, then attenuation here, and then reflection and transmission here. Okay, you got that point? So inshallah in the next class we will be talking about these last two concepts: the principle of attenuation, yes, principle of attenuation, and some important safeties features, and the machine or that device which is used to produce ultrasound. Okay, till this point any confusion or you want to ask me anything, please, I'm here.